Today we are performing another topology optimization tutorial with Nastran Solution 200. My name is Christian Aparicio and I'll be helping you with today's tutorial. This one's going to focus on mirror symmetry constraints. So this is what you can expect by the end of the video. We are going to start with this original design that you see here on the left, and we are going to use the topology optimization technology to identify which elements could be potentially removed from the design. So here we're going to try and minimize the compliance of the structure as much as possible while aiming for a mass target of 60%, or rather we're going to reduce the mass by 60%. One special thing we are going to do is impose symmetry constraints. So here you can imagine here in the middle, we're going to have a center line. Whatever happens here on the left is going to happen also here on the right. Oh no, rather, let me take a step back. The symmetry plane, rather, is going to be defined horizontally. So here you can imagine this is the center line, and whatever happens here will also happen here on the opposing side. And here's a quick agenda. I'll go through how the structure is loaded. I'll then go over the optimization problem statement. This is something very important that you should have before any optimization. This is basically a summary of your design regions, your objective, and your constraints. We're then going to go over how to convert a BDF file to Solution 200. How do we create these design regions, objective, and constraints? We'll perform the optimization, and then we'll view the results towards the end. And as always, if you're an engineer and you have questions, if you want more training, if you want guidance on a topology optimization example of your own, I am here to support you. Send me an email and I will get back to you with the response. Now, if you are a student or engineer and you would like access to the Nastran Solution 200 web app, you can also send me an email with your request and I will get back to you with access. Now, let's quickly go over the structural model. This is a plate, simply supported. We are going to apply a load at the midspan. So here you can see the vector and the red dot and where we are applying the load. Let's quickly go over the optimization problem statement, I should say. This entire plate, if you will, is associated with P shell 1. We are going to set this P shell 1 as the design region. We are also going to impose a mirror symmetry constraint. We are going to, 1, define this coordinate axis system, and number 2, we are going to define the symmetry plane. Here you can see that according to coordinate system 1, the symmetry plane is xz. What about our objective? We are going to minimize the compliance. That's our goal. This is often known as maximizing the stiffness of the structure. And what about our constraints? We are going to say that whatever design is constructed, if you will, we are going to say that that mass should be 40% or 0.4 of the original mass. This, in other words, is saying that we are constraining the final design to be less than, or to be reduced by 60%. Now, quick comment regarding mirror symmetry constraints. I took some time to model this same example without the mirror symmetry and with the mirror symmetry. Here you can see without symmetry across the horizontal line here, you can see there's a lack of symmetry. But once I introduce this symmetry constraint, you can see the top matches the bottom. And that's our goal for today. Now let's talk about the procedure. Step number 1, start with the BDF or DAT file. Let me go ahead and step out. You'll notice that here in Patron, I've already taken time to define my finite element model mesh. All that's left to do is to export the model to a BDF file. Here I've exported it to a DAT file. In this file is the entire finite element model, the position of each element, the loading, the material. This file is currently set to 101. We have to convert this to solution 200. In order to do the conversion, we're going to use something called the Nastran Solution 200 web app. This will take this existing PDF file and convert it to solution 200 that allows you to perform optimization. Let's go through this conversion procedure. During this conversion procedure, we are going to specify the design regions, the objective, the constraints. We're going to export that, run it in Nastran, perform the optimization in Nastran. Then we're going to look at the results. I should mention that at the end of this video, I have a few additional slides that are going over the fundamentals of topology optimization. If you're a new user, there are some commonly asked questions that I think you will find very useful. So again, at the end of this tutorial, I'm going to take perhaps 10, 15, 20 minutes to go through these concepts. Now let's go ahead and start the conversion process. So to start off with, here we are in the web app. If you want to follow along, if you click on the user's guide, there is a topology and topometry tutorial section. This example is this one called Optimization with Mirror Symmetry Constraints. Let's go ahead and just download the file to our desktop so you know that we are in fact following along. So here on my desktop is our starting file. So that would be this file here on the left. Let's go ahead and go back to the web app and click on the topology icon. This will open the topology web app. Let's import this BDF file. Remember, this BDF file is the entire finite element model. We have to convert it from solution 101 to solution 200. We also have to specify the design region, the objective, and then the constraints. So let's go ahead and start with the design variables or region. We'll upload the file. The web app identifies all the regions that can be set as design variables. Here you see it's identified pshell1 as a design variable. Back in Patran, if you go to utilities, properties, property name plot, you can select all the properties here to know what pshell, what psolid, prod, what property type number they might be. Here, this is pshell ID 1. So if I go back to the web app, I find a pshell property with ID 1. So this, if I click the plus icon, it specifies that pshell 1 is now the design region with label X1. So any element that's within this pshell will now be varied by the optimizer. Let's go ahead and move on to the objective. By default, it will automatically set the compliance as an objective. Here it's also set it as rather to minimize the objective. Let's go ahead and move on to the constraints. Also by default, the fractional mass constraint is created for you. Here we are saying that with whatever design is determined, make sure that the mass is, in this case, 40% of the original mass. And here you type decimals to represent the percentages. So again, this is saying whatever design is constructed, make sure that it's 40% of the original, or 0.4. And just a quick change to the last statement, make sure that the mass is less than 40%. Less than because it's the upper bound. Let's see what else. We're going to go ahead and make one last modification. You'll notice that we so far have created the design region, the objective, and the constraints. Let's go to settings and let's change the maximum number of design cycles to 100. And then that's pretty much it. Let's go ahead and download this new version. So you see a new package has been downloaded. If I navigate to my downloads directory, that's where the file is. I'll extract all. In the new folder, let's go ahead and double click Start MSC Nastran, and that will begin the optimization. Here we get a nice status page. And while that's happening, let's go ahead and talk about topology optimization workflows. This is very good if you are a new user to Nastran topology optimization. There are multiple ways of performing topology optimization. There is the so-called traditional, at least I call it the traditional method. There's also the latest topology optimization. This is based on a new capability introduced in MSC Nastran 2016. I'll get to that method in a moment. So with the traditional topology method, the objective is to minimize the compliance. In other words, we want to maximize the stiffness. Our constraint is to say that whatever the mass of the design is, it should be less than a target mass. In our case, we specified a target mass of 40%. Usually, in say size optimization, you see the objective is to minimize the weight. Given the complexities of topology optimization, the preferred and traditional method specifies that the objective should be minimize compliance, not minimize weight. So what's happening here? For this example, this is analogous to our example 2. We went ahead and constructed a design model. So we went ahead and performed the conversion. We then exported it and then performed the topology optimization. This is the topology solution, if you will. If you look at various pictures of topology solutions, they're usually very rough. They're not nice and clean. What you're supposed to do after this, you take that topology solution, you refine it so it can be analyzed. Once you have a refined version of the topology solution, you then perform your verification analysis where you can check things like stresses, displacement, and natural frequencies. Now, in the event that you go through this whole procedure and find out that some of your design constraints have not been satisfied, and here it's actually a checkbox, you would then try a different mass target. So here, for example, this was attempting to only keep 60% of the mass. At the end, it just did not work. So this whole workflow did not work. You then increase the amount of mass you keep. So here, just visually comparing the two, you can see there's more mass in this version. You refine the topology solution, you perform your verification analysis, and then you look at the results, and if they're all okay, that's a suitable design. What you see engineers do, they will create multiple topology optimizations, and they will pick the better of all the combinations they tried. Here you see that this combination produces valid results, so does this combination. So now which one do you pick? This one has a mass of 9.0 grams. This has a mass of 7.739 grams. So since this one's the least in weight, this design in the middle is my final design, and this is the one I'm going forward with. Now, what about the latest topology method? This is more intuitive. Like I said, this was available starting in 2016, I believe. Here, the objective is to minimize the fractional mass. In other words, minimize the mass. So here already, the process is more intuitive. Number 2, you can actually impose a stress constraint. With the traditional approach, it's really difficult to impose a stress constraint. It's so difficult that oftentimes you don't include it. Here with the latest method, you can impose stress constraints. The benefit here is that when you arrive at a topology solution, and then you go through the refining stage, and then you look at your verified results, you are more likely to satisfy your stress, your displacement, and other structural constraints later on. This tutorial is using the traditional method. So now let's go back and look at the results. Once the status page is finished, it will automatically open this results page. Be mindful of this message that says run terminated due to hard convergence. The green checkbox indicates that this is a successful optimization. Here you can see that the objective to minimize compliance is 0.79, and it was reduced to a value of 0.0879. So now that we know that the optimization went through successfully, let's look at the topology solution inside of our post-processor. Go to Tools, Design Study, Post-Process. There's one file in this folder, and it's called DES. This file contains normalized material densities for each element. Think of these densities as ranks. The higher the rank, the more you should keep that element. The lower the rank, the less you should keep that element. So let's go ahead and import this DES file. And once we import the file, we'll go ahead and display the results. So we'll go ahead and click on display. We'll select this case. And for the threshold, I'll type in a 4. And then we'll go ahead and click on the fringe just to see that. So here I neglected to include something, and that is the symmetry constraint. So let's go ahead and actually do that right now. We'll go to variables. If you want to include symmetry constraints, click on the options of step 3. And here, mark the checkbox for symmetry constraint columns. This is where you can say yes, turn on symmetry constraints. For the coordinate axes, here if you zoom in, you can see that this coordinate system, we want to model this about the ZX plane. So here you can see the coordinate system has an identification number of 1. So we'll go ahead and type in 1 there. We'll mark the ZX plane, and then we'll ignore the last 2 columns. So let's go ahead and output this new directory. Let me go ahead and just delete the old files. And then this one, I'll just rename it right now. This is called FR Mass 40%. So let's go ahead and extract this and perform the optimization. And we'll go ahead and click run there. Remember that with the traditional approach, which is this one, you're going to try different fractional masses. So let's go ahead and do that right now, just to show you what the procedure looks like. Here, this is 40%. We'll go ahead and try one that's 60%. We'll go ahead and export this version. Here, I'll go ahead and rename this one FR Mass 60%. And then we'll go ahead and create one that's 80%. Remember, the fractional mass says that whatever design that's proposed by the optimizer, make sure that the total mass is a fraction of the original mass. So here, this one's going to be 80%, so you can definitely bet that the design at the end will be 80% of the original mass. So now here, the version that is 40% fractional mass has finished. Here again, be mindful of this green checkbox. It indicates that a successful optimization has been performed. Let's go ahead and now go back to Patran, and we'll go ahead and re-import the results. And we'll go ahead and see what has happened. So tools, design model, post-process, read results. I'll go ahead and select this new directory, 40%, and click apply. After this, we'll go ahead and say display results. And then this one's going to be the second version that you see here. And we'll go ahead and click apply. So here we go. Here's the result we wanted to look at. So instead of doing this, let me see if I can do it another method. I'll try something really small. So here you can see in topology optimization, elements are never removed from the actual model. You are instead given a ranking system, or in other words, a normalized material density for each element. Densities that are close to 1, here you can see they're colored in red. These are elements that should definitely be kept in this proposed concept. Normalized material densities that are close to 0, that are close to white, are elements that could potentially be removed. They're not doing a lot for the stiffness of the structure. Here I've actually created multiple topology concepts. Let's go ahead and see which one could be the one. So this is a good starting point here. This is where you take this concept, you refine the design like I mentioned earlier. You take these jagged edges that you see here. Of course, this is a different example, but the same procedure applies. You try and smooth out the mesh. After you're done smoothing out the mesh, you then perform your final verification analysis where you confirm that it's passing your stress, displacement, and other structural requirements. One thing you saw me do in this tutorial, I created multiple topology versions, each one with a different fractional mass. And that's because you want to try different combinations. And then at the end, whichever one passes all of the requirements, you just pick the best option out of all of them. And that's the one you take as your final solution. So here is the end of this tutorial. Here you can see the different packages that I can extract and run each one individually. I can then do the whole procedure with Patran, show the concept, and go from there. I think at this point, we are at the end of this tutorial. As promised, I'm going to go over some commonly asked questions in a moment, but a quick reminder for those that have to go. If you're an engineer and you want to start performing topology optimization, if you want some training, feel free to reach me at this email address and I will get back to you with some resources. Now, if you're a student or engineer and you want access to the web app that will help you set up and convert to Solution 200, also contact me at this email address and I will grant you access. Let's go over some commonly asked questions. What are the design variables in topology optimization? To be frank, they are named normalized material densities. Here, for example, let's suppose this entire plate started off with the density of 1,000 kilograms per meter cubed. What happens in topology optimization, this one density that was shared for all the elements, it's broken apart. So now this element has its own density and density I. Here, this density could be density 2. This density for this element could be density 3. Now, how is this density that's in units of kilograms, meters cubed, or density units, how is this related to a normalized material density? So we'll go ahead and let rho n represent a normalized material density. We'll say that it's equal to 0.5. Now, how is this related? Here at the top, we have the material or the normalized material density for this element. If the original density was 1,000 kilograms per meter cubed, then its actual density is 500 kilograms per meters cubed. So it's this variation in these design variables that contribute to the stiffness of the structure, and it's through this that the optimizer is able to perform the optimization. Here, this spectrum that you see here in red and white, this is a plot of all the normalized densities. So it's essentially a plot of all the design variables. I usually like to call these design variables ranks. Anything that's close to 1 means the elements should be kept. Everything close to 0 are elements that probably you can dismiss. What is compliance? Here in the F06 file, you'll find a section called element strain energies. Here is a value for this example. We only have one load case, so there's only one value for total strain energy. Here you can see the value is 0.397, so it's about 0.4. If we look here at the compliance for for the very initial design, it's approximately 0.8. So you can see that the compliance is twice as big as the strain energy. So in effect, what we're doing when we say we want to minimize the compliance, so here we'll have an arrow pointing down, we are actually minimizing the total strain energy. And of course, this is the same as saying that we're increasing the stiffness of the structure. And just in case anyone's wondering why I'm writing as if I was 5 years old, I'm using a mouse. Now, here on the left, I just have some other comments. Feel free to pause the video and read over those comments if you're interested. I basically it's just a repetition of what I just said and some sources if you want to read up on this more. On this slide, I just have some instructions on how to output this information in the F06 file. What is fractional mass? Let's go ahead and take a quick example here. Let's suppose we have a plate composed of 6 elements. So here, element 1, 2, 3, 4, 5, and 6. It has a mass of 6 grams as an example. This 1.0 is going to represent its normalized material density. So this is the so-called, I shouldn't really call this the initial design, but this could be the starting design, if you will. And you'll notice that if we specify that the upper bound for FR mass is less than 0.3, if this was our starting point for the topology optimization, the FR mass is 1.0. So this is already violating this initial constraint, which is not a good thing for the optimizer. So what happens in the background, there's a step I call reduction. Nobody calls it reduction. If you read the manuals, if you read papers, nobody really calls it a reduction. I just call it a reduction, so it makes sense to you. What happens here is that each normalized density that was a 1 is reduced. So here, if the FR mass is less than 0.3, remember this FR mass is given here. So here it's 0.8. So here, let me change it back to 0.3 so you follow along. So here it's 0.3. What happens in this reduction stage, it takes each normalized density of 1 and reduces it to 0.3. So as an example of the density before it was 1000, but then you reduce it by 2.3, then the density is now 300 here kilograms per meter cubed. So it will do this for each element. It is from this reduced state that it actually starts the optimization. It starts from here because the total mass here, the total mass is 1.8 before it was 6. This total mass, because of the reduction in the material densities, is now 30% of the original mass. So here the FR mass is less than or equal to 0.3. So here the constraint is satisfied. Remember, before it was violated. So this is the starting point for the optimization, this reduced state with the reduced material normalized densities. So now fractional mass. Fractional mass is just a number that represents how much material was kept. So here in this case, the fractional mass is 0.3, so 30% of the material was kept. If we are saying that the FR mass is always less than 0.3, this is saying that any design that's proposed at the end of this topology optimization, it should be less than 0.3, or rather, we should always have less than 30% of the material. The optimizer, what it will decide if it should minimize some of these material densities or if it should increase the material densities. Here you can see that at the end of the optimization, we can have different material densities like we did a moment ago. It'd probably be a good idea to show you those spots. So here we can have something that's very close to 0, or we can have something very close to 1.0 here. At the end of this optimization, you'll notice that the mass is still 1.8 grams, which is still 30% of the original mass. And this is still satisfying the constraint of FR mass is less than an upper bound of 0.3. Now, how is it possible to increase the stiffness? Since we reduced the model, we've effectively softened the model. This is where it's going to modify each design variable. It will either increase the design variable or it will decrease the design variable to maximize the stiffness. Here, by the end, you can see that it's identified regions where the material has a really low normalized material density, and these regions can be effectively removed. And one last comment, the threshold. Back in Patron, I specified a threshold of 0.4. What is this 0.4? Here on the right-hand column, this spectrum that you see here is the range of normalized material densities. The 0.4 is effectively a cutoff. Anything above 0.4, you're going to keep. Everything under that, you're going to say ignore or remove. RE. So here, this is before applying the threshold, and this is after applying the threshold. You can see it's removed all the elements that are less than 0.4. So again, this threshold is a cutoff point for the normalized material density. I believe that was the last slide, so I think it'd be worth showing my contact information as the last slide. A quick reminder, thank you for watching, and if you're an engineer or a student, you're always welcome to send me an email with your optimization question.